Hello, everyone. So welcome to tonight's live stream. Before I make the same mistake I did last time, I'm actually going to check my sound levels uh, myself. So just give me 1 second here, because I can listen to my own stream. It gives a bit of feedback, but it's better than speaking and not having any audio. Okay, we're good. All right. So what are we doing tonight? We're going to go over the first half of the magnetism that we've been studying, and that's on the sources of magnetic fields, which are currents, and also what the forces that are caused by magnetic fields, and that's the Lorentz force. Okay, so there's two topics, although they're like broken up into multiple different problems. So the first one is, where do magnetic fields come from, and that is from currents, and there's some formulas for that. And then the second one is, once you have a magnetic field, what does it do? Well, it exerts a force on currents. Okay, and that's the Lorentz force. All right, so let's start. So question number one is, what is the magnetic field? 1 millimeter from a wire carrying 10 amps. Okay, so if you have a single wire, and you'll actually do this in the lab, I guess, next week, when you have a single wire, and you put a current through it, you'll get a magnetic field generated around it. And the magnetic field is not parallel to the wire, it's actually perpendicular to the wire, and it circulates around the wire. Okay, but we'll look at that in the next problem. Okay, the formula for that, I have it written here. It's B is equal to mu naught, which is the permeability of free space. Okay, so remember, in electricity we had this epsilon naught, and that was the permittivity of free space. This is the permeability of free space. Everyone confuses the names, so don't worry about that. But the symbol is mu naught, and it has a value. Okay, I is the current, which in this case is 10 amps, and divided by 2 pi, and then R is the distance from the wire. Okay, so let's do that problem. Okay, so B is equal to, and let me quickly look up that value for the I think I remember it, but I want to make sure I don't make a mistake. Permeability of free space. All I'm doing is just getting on Google, and wow, that's a long number, a lot of digits there, but I'll give you all the digits. Here, let me write this. That's way too many digits for us, but nonetheless, there it is in MKS units. Okay, and these are, they really spelt out the units, but the way we should probably think about this is in terms of Tesla meters per amp. Okay, and that's because magnetic field is in Teslas, and the I there will carry units of amps, which will cancel the amps in the denominator there, and R is in units of meters, which will cancel the meters there. Okay, so now we're ready to do the problem. All right, B is equal to, and we'll just keep a few digits here. All right, times 10 to the exponent negative 6. There you go. There's your mu naught. I is 10 amps. All right, divided by 2 times pi, which is 3.14, times, let's space that out a little bit so you can see it better. All right, times R, and R is, how far are you from the wire? Well, 1 millimeter, but in meters, that's going to be 0.001 meters, like that. Okay, so what's that going to equal? Let me work that out. It's equal to this number right here. Okay, and too many decimals again, so we'll just round it off to 3 significant figures. Okay, and the units are going to be Teslas, and this worked out very nicely. If I move the decimal over 3, 1, 2, 3 places like that, I'll get 2.0 milliteslas. Okay, and that's actually a reasonable number. Okay, a millitesla is it's a little bit big. I mean, the Earth's magnetic field is about 65 microteslas, so this is much bigger than that. But because milli is 10 to the minus 3, micro is 10 to the minus 6. But it's not a huge number. Okay, it's something that's doable in the lab. All right, there's our first problem. It's a very easy problem. There's not much to the questions to the question, what is the magnetic field caused by a wire? And it is important though, because that's how magnetic field, the relationship between electricity and magnetism was discovered, was by Ørsted passing a current through a wire and noticing that it deflected a compass needle. Okay, now the formula isn't hard, but you know what's kind of hard about these problems is the direction of the magnetic field, and I'll draw it in a minute. But before I do, like on the test or on the assignment, I'm just going to give you a verbal statement of the right-hand rule. And there's actually 3 versions of the right-hand rule. They're all related to one another, but there's 3 versions. One is, the direction of the magnetic field for a straight wire, which is what this question is. And there's one for the solenoid, and then there's another one for the Lorentz force. But question number 2 here is, what is the right-hand rule for a straight wire carrying a current? Okay, and it basically, the right-hand rule states that if you point your thumb in the direction of the positive flowing current, okay, so you might remember from when we did voltages and currents, when we first came up with currents, we actually looked at the positive. They thought that it was positive charges that carry the current. It's actually the negative. So you always draw the current in traveling towards the positive. Okay, I'll indicate that in a diagram. So you point your finger in the positive direction of the current, and the fingers of your right hand, maybe I'll do it this way. So imagine the current is going up. Okay, so I'm going to point my thumb up, and this is my right hand, and then the fingers of my right hand would curl around like that, and that's the direction of the magnetic field. See how my finger is pointing that way? So the magnetic field is, let's turn it this way. Magnetic field is like that, okay? The direction of my fingers. All right, so let me try to draw that for you. Oh, whoops. Oh, there it goes. Okay, took a second to pop up. Okay, so suppose you have a wire. So here's the wire like that, going straight up like that. Okay, and that's like the positive flow of current. Okay, so you can imagine like even though it's the electrons, you can imagine little positive charges, and they're actually traveling up like that. Okay, all right, now if you point your thumb in that direction, what direction would the magnetic field be in? Well, here's what's difficult about magnetic fields is that they're in 3 dimensions, and what you're seeing in front of you is a 2-dimensional surface. And so how do you draw that? So the way I draw that is I draw like, it circulates around like this, but I'll break it in the back here. Notice how I have a little break right there in that blue circle, and that's the only way that I can indicate that that's the back side of the loop. So this part here is the back of the loop. And of course, if that's the back of the loop, because it's going behind the wire, so you can see that it kind of breaks there. So this is the front, like that. All right. And using the right-hand rule, I mean, there's 2 possibilities. Either it's going to go that way, and that's wrong, or it's going to go this way, and that's right. Okay, that's the one that the right-hand rule says. Okay, it says that it's going to circulate like that. So behind, and then in front, and then behind, and then in front, like that. Okay, all right, good. So there we go. There's our first 2 questions. Okay, let me take a look at the chat here. All right, a few people on. All right, I don't see any questions though. Great. Let's move on. Now, a straight wire will certainly produce a magnetic field, but the most efficient way of producing a magnetic field is with a solenoid. And a solenoid is basically a coil of wire, okay? And you'll see those in the lab. I think you'll see those in the lab. Yeah, you will. In the magnetic lab, you'll see a solenoid, okay? And if you put a current through that, you'll produce a magnetic field. Inside the coil, the magnetic field is constant, which is very nice because it means that you can do some simple calculations. Outside, the magnetic field flares, and so it's a much more complicated formula for that. But we're just going to look inside. And so the formula for the magnetic field inside a solenoid, okay, so that's important that it's inside, not outside, is basically B, the strength of the magnetic field in Tesla, is equal to mu naught, the permeability of free space, I, the current, N, which is the number of windings, number of turns, and the to make the solenoid, because it is, you keep looping them over and over and over again. It's a coil, and L is the length of the solenoid. Okay, so you're looping like this, but how long is it? Okay, and basically, the shorter the solenoid, the more dense the turns are, and so that's why it's like n divided by L. Okay, and the smaller n divided, sorry, the bigger n divided by L is, the bigger B will be, and so conversely, the smaller L, the bigger B. Okay, so let's read the problem. What is the magnetic field in a 1.5 centimeter long solenoid made with 500 windings of wire when a 500 milliamp current is applied? Okay, and assume there is no core, because to enhance the magnetic field, what you do is you put something like iron in there, okay, or nickel or something like that. And these are materials that enhance the magnetic field, and that's how you actually can make an electromagnet to pick up things. Okay, and you might have seen these huge electromagnets that are actually used to lift cars, and you go, could you really do that? Yeah, I mean, iron enhances the magnetic field so much that, you know, when you put enough current there, you can actually produce strong enough magnetic fields to like lift large metal objects. Okay, this one though does not have a core. Okay, and so there's the formula without the core. The next one is the same problem but with the core. Okay, so let's do this one. All right, so B is going to equal, well, there's that permeability again. There it is. Okay, multiplied by I, current, and I tell you the current is 500 milliamps, which is 0.5 amps. Okay, and you know what? I'm going to put the units in here just to show you how they cancel out. Okay, so there's the units for the permeability. N is just a number. It's got no units, so it's just this 500 right here. Okay, so there's 500 there like that, divided by, and 1.5 centimeters is going to be 0.015 meters. Okay, and let's take a look here. Notice there's a meter in the numerator here, and it'll cancel against the meter in the denominator there, so the meters cancel. And here there's an amp in the denominator, and here's a amp in the numerator, or sorry, the other way around. Numerator and denominator, they cancel. And what unit are you left with? Just a Tesla, and a Tesla is a measure of magnetic field. Okay, magnetic field strength. Great. So let's take this and calculate it. All right, so that's equal to this number right here. Let me put it on the next line. B is equal to that many Teslas. Okay, again, on a test, I probably wouldn't put a number like that. I'd move it over. I'd move the decimal over 3, and so it's 21 milliteslas. There you go. So, all right, not a very big magnetic field. Certainly big enough that you would deflect the compass. Okay, because again, the Earth's magnetic field is like 65 microteslas. Okay, even if it were 20 microteslas, that would be 1,000. So this one would be like 1,000 times more than the Earth's magnetic field. The Earth's magnetic field varies quite a bit. It depends where you are on the Earth. Okay, so anyhow, so that's about 500 to 1,000 times bigger than the Earth's magnetic field. It will definitely deflect a compass needle. Okay, so the next problem is actually the same problem all over again. Okay, and it says what is the magnetic field? 1.5 centimeter long solenoid, 500 windings, 500 milliamps, but this time there is a core, and it has a relative permeability of 750. Okay, and this relative permeability, all it means is just the enhancement factor. That's it. It just means that this magnetic field is going to be 750 times bigger than if there were no core. Okay, and so really you don't even have to really to recalculate everything. I think in the lecture, I think I called it MR for mu R for relative. Okay, but there's nothing much to calculate in our case, because we already calculated this piece. That's the 21 milliteslas, and this is 750 there, so we're going to have 750. That's our 750. That's our relative permeability multiplied by mu naught I N divided by L, but we did that already. Okay, it's the exact same numbers as right up here. Okay, and that turned out to be 21 milliteslas, like that. And so what's that going to equal? So that's going to be, multiply that by 750. Whoops, let's do this right. And it turns out to be this. Now, you know what? Actually, let me switch back to 0.021. Okay, so there we go. So 750 multiplied by 0.021 Teslas, like that, will give you 15.75 Teslas. Okay, now this is striking because 21 milliteslas is kind of small. Uh, it's much bigger than the Earth's magnetic field, but it's still relatively small. I mean, maybe you can pick up paper clips like this, but you're not going to be able to do much more. But 50 Teslas is huge. Okay, um, I think the biggest magnetic field that I've ever like worked around was a 7 Tesla magnetic field. Okay, and so 15 Teslas is a lot, and you would certainly be able to pick up something metallic with this pretty easily and exert a lot of force. Okay, but take a look here. It's this solenoid's only 1.5 centimeters long. I mean, it's a pretty small solenoid, but it has this core with a relative permeability of 750, and it'll enhance it by 750. Now you might say, are there materials that do 750? Yeah, I mean, I think iron is 1500, so 1500, twice that. Okay, so yeah, there's some materials that really enhance the magnetic field. Okay, all right, so there's question number 4, and this brings us to question number 5. So in the previous question, I just asked for the magnitude of the magnetic field, but a magnetic field is it basically is a vector. Okay, it's a field of vectors, and so you should be able to say what direction the vectors are in. So here's the right-hand rule, but this right-hand rule is a little bit different. And maybe I should put, you know what, let me put these two side by side. Okay, I'll put these two side by side. All right, like that. So what's the right-hand rule for a straight wire? So it's point thumb of right hand, of course, in the direction of the current, and fingers point in the direction of the field. Okay, that's for a straight wire. For the solenoid, it's the other way around. You point your fingers in the direction of the current, and remember they're coils. Okay, so and then your thumb of the right hand, of course, fingers of right hand, fingers of right hand. So point the fingers, point fingers of right hand in the direction of the current, thumb points in the direction of the B field. Okay, so notice it's kind of opposite. Okay, so once again, for the straight wire, you point the thumb in the direction of the current, and the fingers point in the direction of the field, okay, the B field. Here, for the solenoid, you point the fingers in the direction of the current, and the thumb points in the direction of the B field. Okay, technically speaking, they're the same, and you can show that they are equivalent rules. In other words, there's no violation of like the idea of Ampere's law. Okay, there's no violation of Ampere's law, but because the topology, the shape of these things are different, you know, they result in these different applications of the right hand rule. Okay, let me draw that for you. All right, so over here, let me create another whiteboard. There we go. So now this one's even harder to draw because I got to draw a coil, and you see, how do you draw a coil in 3D? So there's a wire, and see how it's breaking there? So that's the behind. Okay, and like that, and like that. All right, and this is the direction of positive, like that. So that's the positive current. Okay, the positive current is going to travel that way, and this side right here, that side there, that side there, that side there, that's the front. Okay, so notice that this coil, the current comes down, and it's going down in the front like that, down in the front like that, down in the front like that, and it's going up in the back up in the back, up in the back, like that. Okay, so yeah, a bit messy. Let me get rid of some of those arrows there, like that. And now let me show you how to do that. So try to keep this image in mind while I show you how to point your fingers. In fact, it's probably best if you think about the back. You know what? Let me get rid of these in the back. So in the front, the current is going down. In the back, the current is coming up. In the back, the current is coming up. In the back, the current is coming up. Okay. Just remember that in the back, the current is coming up. So now, here's my hand. It's either going to be this way or that way. Okay. So so see, in the front it was going down, and in the back it was going up. Okay. And so you can see my thumb is going to be pointing that way. Okay. I think I have that right. I might be having a mirror image. You might be seeing a mirror image. Okay. So, but again, the current down in the front, up in the back, down in front, up in the back, and then the thumb points that way. Okay, thumb points that way. Yeah. All right. So over here, when we switch to the whiteboard, the pointing the fingers up in the back or down towards the front, you're going to get a B field. Let me do that in red, which is going to be this way. Okay, like that. So I hope that isn't too confusing. I mean, like, I can't do both the whiteboard and my thumb at the same time. But, well, maybe I can just do this. Let's see here. Oh, no, you get the mirror image. That's the problem. Yeah, you're getting a mirror image. Okay. Yeah, there's no way to do this easily. Okay. So right now, just, I mean, imagine pointing your fingers up in the back, and then your thumb is going to be pointing to the to your right. Okay. And that's how you apply the right hand rule on a solenoid. Admittedly, not that easy. Okay, I admit that's not that easy. Okay, but on a test, I probably wouldn't give you a diagram. I'd probably just ask you to, just like I did in the assignment, I'd ask you to, be able to state it, or it's multiple choice, but be able to pick out the correct statement of the right hand rule applied to a solenoid. Okay, so all right, let's see what's going on in the chat here. 3 people watching. All right, no questions though. Great. Let's go on. Okay, so up to this point, we did currents create B fields. Okay, that's basically Ampere's law. All right. And a full statement of Ampere's law, of course, is not something I could give you, either the calc or non-calc based, because even the calc based probably can't do vector calculus. Okay, and it requires vector calculus. That is basically integration of vectors. Okay, now once you created this B field, what can you do with it? Okay, I kind of alluded to the fact that you could pick up things with an electromagnet, but how does that work? Well, whenever you're picking up something, it's like pulling, right? And pulling is a force. And so magnetic fields exert forces on things. What kind of things do magnetic fields exert forces on? And the answer is on currents. Okay. Now think of a current as either like a wire carrying a current, or it could be just a single charged particle moving through a magnetic field. Okay. And if a current travels through a magnetic field, then the magnetic field is going to exert a force on that current. And that's called the Lorentz force. So the remainder of the questions are going to be about the Lorentz force. Okay. So let's start off with the first question here, number 6. What is the force on a wire carrying 750 milliamps in a 2.5 Tesla field if 10 centimeters of the wire is in the field? Okay, and the wire makes a 35-degree angle with the field lines. Okay, now let's go through this. Let's go through each of the pieces. Okay, so the force here is going to be proportional to the current. Obviously, the more current, the more force there is. The force is also going to depend on the strength of the B field. Obviously, the stronger the B field, the more force. Okay, but then there's this L. Okay, and L is how much of the wire is in the B field. Okay, so if the B field only covers a little bit of the wire, then it's only going to exert a force over that little bit of the wire, and it kind of exerts a force per unit length. So if it's only a short length, it's only going to exert a small amount of force. If it's a large length, then it's going to exert more force. Okay, so that's why there's an L there. And also there's an angle, and this is important. The most you're ever going to get, the most force you're ever going to get, is when the current and the B field are perpendicular. Okay, if the current and the B field are parallel, there is no force at all. All right, it might seem counterintuitive, but that's just the way B field works. B fields work when they're crossing things. Okay, and so if there's a 90-degree angle, that's when you're going to get the most. If there's 0 degrees, you're going to get nothing, and everything in between is sine theta. Okay, so now we can go ahead and plug into this. So let's go ahead and do that. The force is going to be the current, and I told you the current was 0.75 amps. Okay, because 750 milliamps is 0.75 amps. Okay, great. Now L is the length, 10 centimeters here like that, and 10 centimeters is 0.1 meters. Okay, I'm putting the units in there on purpose. All right, you'll see why. And then the B field I told you was 2.5 Teslas. Okay, and finally sine, and I decided to make it 35 degrees. So it's going to be sine of 35 degrees like that. Okay, now let me isolate the units for you. So let's take this, and so let me bring out an amp out here, and then there was a meter there. Okay, so let's get rid of that meter there and put it out here, and then this Tesla here, I'm going to put that Tesla out there like that. Okay, so those are the units: amp, meter, and Tesla. Amp, meter, Tesla. Okay, and you might say, well, why did you do that? Because that's the units on the right hand side, and what are the units on the left hand side? A Newton. And so this is probably the best way to think of a Tesla. Okay, well, let me rearrange it a little bit. If I just divide both sides by AM, then I get this formula here. Okay, and that says that a Tesla is a Newton per amp meter. Okay, and the Lorentz force kind of explains to you what a Tesla is. A Tesla is 1 Newton of force for 1 amp on wire carrying 1 amp, 1 meter of that wire per 1 meter. Okay, so let me say that again. For every meter of the wire carrying 1 amp in a magnetic field of 1 Tesla, you'll get one. In a 1 Tesla field, you'll get 1 Newton per amp per meter. That's the way to say it. Okay, so that's how big a Tesla is. All right. So because otherwise, the way I introduced Tesla before from Ampere's law wasn't clear what a Tesla is, but now it's kind of clear. You get 1 Newton of force for a wire carrying 1 amp per meter of that wire. Okay, in a 1 Tesla field. All right. So let me work out this number here. Okay, calculate it for you. And malformed expression. How come? Is that a malformed expression? Oh, I see why. Okay. There we go. All right, so we get that F is equal to this number right here, newtons, okay? Or rounding it off, 0.108 newtons or 108 millinewtons, okay? So it's not a lot of force, not a lot of force. All right, that answers that question, okay? And what's the right-hand rule for the Lorentz force? So the Lorentz force also has a right-hand rule, but it's different than the other ones. Basically, what you have to do is realize that the force is always going to be perpendicular to both the B field and the velocity. Okay, so two vectors which are not parallel to one another, but two vectors which are like at some angle to one another, they always form a plane. Okay, basically a plane like that, whatever direction. The force is always perpendicular to that. Now, there's two possible perpendicular directions, all right? And you have to pick between the two. And here's where it gets a little tricky. You have to imagine that the velocity vector is kind of like the dial on a clock, and then you just turn the V to the B field, and then your thumb will point in the direction of the force. If it's a positive charge, and if it's a negative charge, you got to change the direction. Okay, let me try to draw that for you. All right, so over here, create a new whiteboard. All right, so again, this is in 3D, so it's kind of hard to do. Imagine that the velocity is directly along the paper here like that, or the screen, okay? Imagine that the B field is actually pointing out towards you. So what I'm going to do is I'm going to draw it like this. Okay, and you say, geez, what is that? That's supposed to be like a vector pointing straight out at you. So imagine that that's coming out towards you, okay? And that's the B field, okay, like this. And you say, all right, so it forms a plane. It forms a plane. Well, here, let me show you. It forms a plane kind of like this, okay? So velocity was this way. Oh, I'm getting the mirror image again. Okay, let me see if I can. Velocity was that way, and the B field is out towards you, okay? So velocity and B field forms a plane like that, okay? It lives inside of a plane like that, okay? And now you say, well, the force, what direction is it going to be in? So the force, let me do that, I guess, in green. It's perpendicular to both V and B. So it's either going to be up or it's going to be down. And I don't know how to draw down here without clobbering my B field like that, okay? And you say, well, which one is it? Is it up or is it down? Okay, let me clean that up actually. Okay, and the way you do that is you say, you know what? Imagine that V gets turned to B like that. Take your right hand and point your fingers of your right hand in the direction of the turn, and guess what? The B field, the force will be straight down, okay? Because your thumb will point straight down, and so the force in this case is going to be straight down like that. Okay. Once again, imagine that you're pointing your fingers. So the tips of your fingers are like at the edge of at the tip of the arrow right there. That's where the tips of your finger are, and your palm is over here for your right hand. Your thumb is going to point down. That's the direction of F. Okay. That's if it's a positive charge. What if I given you a negative charge? Well, then it would be up like that. The force would be up for a negative charge, okay? Admittedly, the hardest of the right-hand rules, okay? So let me try to write it in English. This way I both drew it for you, and also I can give it to you in English, okay? So the first thing you realize is that the force, let's just say F, is perpendicular to both V and B, okay? So this is probably the most important part of it, okay? Because it tells you one of two directions, okay? And then the next part is, how do you decide which of those two directions it is? So point the fingers of the right hand in the direction that V turns to B, okay? It's called a curl, actually, if you want the mathematical term. So, imagine the direction that V would turn to B, or rotate to B. Imagine, you've got V and you're going to just start turning it towards B, okay? And as you turn it, there's a sense, okay? You point your fingers in the direction of that sense, of that turn, and your thumb will automatically point in the direction of the force, okay? And thumb of right hand then points in the direction of F for a positive charge, else it points opposite F for a negative charge, okay? So there you go. There's the right-hand rule applied to the Lorentz force. Okay. So, I didn't ask in this problem here what direction it would be. And I didn't even ask it in the other ones. It's I don't know. It's a difficult Lorentz. The direction of the Lorentz force is kind of hard to ask questions of because it's hard to draw the pictures. Okay, but you should definitely know how to state it in English. Okay, all right. Let me see if there's any questions in the chat. Nope. All right, so let's go on. Now, in the next two problems, we're going to, rather than having the current in a wire, we're going to have a single charged particle entering a magnetic field. Okay, so question number 8, it looks like there's a lot of information there, but it's actually, the answer is very simple. And let's read it and you'll see why the answer is simple. So a particle with charge Q is equal to, whoops, I better give you the charge, and I don't know why I have the mu there. Let me just copy a mu from up here. There we go, paste it there like that. Okay, so we have a charge which is plus 3 microcoulombs, and it has a mass of 1.5 grams. Okay, it's traveling with a velocity of 10 meters per second and a 7 Tesla magnetic field. If the velocity is parallel to the field lines, okay, what is the acceleration of the particle? What is the cyclotron radius and frequency? Okay, let's start off with this. What is the acceleration of the particles? Okay, so one way you can write the Lorentz force for a wire was this formula here. But during the lecture, I showed that that formula is actually equivalent to this formula. Okay, so the previous formula is appropriate for a wire. This formula is more appropriate for a charged particle. Okay, great. So now what? Q is the charge, V is the velocity, B is the magnetic field, and theta is the angle between the velocity vector and the magnetic field. But look at what I said here. I said in this problem, if the velocity is parallel to the field lines. If V is parallel to B, that means they're both in the same direction. That means that there's no angle between them. So that means that theta is 0, and so what's that force? That force is 0, and if that force is 0, that means that the acceleration is 0. Whoops, I forgot a divides. There we go, like that. Okay, so I guess I could do that just very quickly here. I don't care what Q, V, and B is. All I know is that we're doing sine of 0 degrees, okay? And sine of 0 degrees is 0, all right? Because why 0 degrees? Well, that's what parallel means. When you say that V and B are parallel, it means they're in the same direction, it means there's no angle between them, and so there's no force, okay? So the point of this question is to show you that that direction is critical, okay? And so you could have all this extra extraneous stuff going on, but the mere fact that the velocity and the B field are in the same direction means that you're not going to get any force, you're not going to get any cyclotron frequencies. Cyclotron frequency is the frequency or the radius at which something does uniform circular motion. This is not going to be doing uniform circular motion, and that's it. Okay, so this problem was a little bit of a, I wouldn't say a red herring, but I just wanted to make sure that I emphasized that when V and B are parallel, there is no force. The next question is identical, but let's see how I wrote it. I said this time the velocity is perpendicular. Okay, so let's go through it. So the first question I ask is, what's the acceleration? You say, well, how do I get acceleration out of this? Well, if you have the force, and you divide the force by the mass, you get the acceleration. Okay, and so let's calculate the Lorentz force first using this equation right here. Okay, so the force is equal to, I didn't do this problem before, so I don't know how big or small these numbers are going to be, but we'll find out. Okay, and I guess I can get rid of that mu and put in a proper mu. Okay, like that. And it is positive. I did want to make it positive. Okay, not that it makes that much difference, but so Q is 3 microcoulombs, like that. Okay, and we'll convert that to MKS in just a second. The velocity is 10 meters per second, like that. The B field is 7 Teslas, all right, like that. And then you get the sine of, and now we're perpendicular. And perpendicular means 90 degrees, and the sine of 90 degrees is 1. Okay, so F is going to equal, well, 3, the micro, so coulombs is MKS, but not micro. The micro is times 10 to the negative 6. Okay, and then 10 times 7, like that. All right, and whoops, that's going to give us our force in in newtons. Okay, this is going to be a fairly small force, but let me do that. So here it is. Okay, and that's in newtons. All right. Now, I mean, I could convert that to, I could convert that to million newtons or micronewtons, but that's okay because they didn't ask you for the force directly. Now I want the acceleration. Say, well, how do you get that? Well, that's just Newton's second law. So there's that second equation right there. Okay, so the force is this number divided by the mass, which is 1.5 grams, but 1.5 grams, that's not MKS, okay? So you want to do kilograms, and if you're going to, so kilo is like multiplying by 1,000. Here, let's do it this way. So we got 1.5 grams. If I multiply by 10 to the negative 3, and I multiply by 10 to the 3, like that, okay? So what did I do there? I've got 10 to the minus 3 and 10 to the 3. Well, 10 to the minus 3 times 10 to the positive 3, you add the exponents at 0, 10 to the 0 is 1. So basically, that I didn't change anything. It's like multiplying by 1. But the 10 to the 3 part, that's the kilo part, like that. Okay, so basically what I have here is how you convert this to kilograms. Okay, no, just another way to say it is just move the decimal to the right 3. Okay, and so this is going to equal this number here in MKS, okay, divided by this number here in MKS, like that. All right, and what's that going to equal? That. Okay, so 0.14 meters per second squared. Okay, why meters per second squared? Well, it's an acceleration, right? It's an acceleration here. Oh, an acceleration, and acceleration in MKS is meters per second squared. Okay, so not a lot of acceleration, but it's something. It's definitely going to deflect the particle. Okay, and now let me show you what happens when you've got a charged particle in a magnetic field. Okay, so let me just draw another picture. So I did draw this in the lecture, but imagine that the B field is coming out at you. So over here, let's do that in B is up out of the screen. Okay, so it's coming straight at you. Okay, usually that's drawn as like a dot like that. Okay, if the B field were going into the screen, you usually draw that. Okay, but not that it's important. But okay, so the B field is straight up at you. Okay, and you have a velocity like this. Okay, so there's your velocity. All right, and you ask the question. Let me draw it a little bit longer, like that. You ask the question, which way is the force? And remember, this is a charged particle. You would turn the V, which is straight up, towards you. Okay, and that means that your finger, your thumb, would point this way, like that. Okay, so the force, since it's perpendicular to the V, what's it going to do? Well, it's going to deflect the V. So I drew it straight here, but what's actually going to happen is the V is going to turn, okay, like that, because the force is turning it that way. Of course, as soon as it turns and you do the right-hand rule again, guess what? Now the force is this way. And what does that mean? It's going to turn some more. And it's going to turn some more. Whoops, like that. Turn, 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 turn. And what's it doing? It's doing uniform circular motion, okay? So there you go. So this is going to start doing uniform circular motion. All right. So that's what happens when you fire a charged particle into a magnetic field with a velocity perpendicular to the field. It goes in. At first it's going straight, but as soon as it starts to feel the B field, it starts to go in a circle like that. Okay. It's kind of cool. All right. It's not what you'd expect. Certainly not the way electric fields work. Okay, great. We've got the acceleration. Now I ask for the cyclotron radius and frequency. You go, well, what is that? Well, that's just the radius, and cyclotron just means that it's due to a magnetic field. But that's just the radius and the frequency of the uniform circular motion. And we had these equations, okay? And they're actually from last semester, but they apply here, so let's use them. So to get the radius, this is probably the one you want, okay? A is equal to v squared over r. But since you want the radius, you want to rearrange it, so you're going to get r is equal to v squared divided by a. Okay, so what did I do? I multiplied both sides by r, divided both sides by a, and that gives me that r is equal to v squared divided by a. Okay, v because in uniform circular motion, v doesn't change. It's uniform. That's what the word uniform means. And I tell you that it's 10 meters per second. So great, we've got the velocity is 10 meters per second. And you want to square that, okay? And the acceleration we found is this, like that. All right. And so that's going to give me a radius of 10 squared is 100, right? And divided by 0.14. And what's that going to work out to? I mean, the answer will be in meters, 714 meters, okay? So that's a huge radius, but no, I didn't do the problem beforehand, but that's what it would be, okay? I kind of expected it to be large, but not that large, okay? So, like 714 meters, that's like 0.7 kilometers, okay? So that's a pretty big radius. All right, and what would the cyclotron frequency be? So then we also had this formula here, from last semester. Not this part here. We had this part. V is equal to 2 pi r over t, where t was the period. But remember, the period and the frequency are related by reciprocals. So I can take out the 1 over t and just replace it with f, and so you get that v is equal to 2 pi f, like that. Okay, let's get rid of the intermediate part here, like that. Okay, so v is equal to 2 pi r times f, which is the frequency, and we don't want v, we want the frequency, so divide both sides by 2 pi r, and we get that f is equal to v divided by 2 pi r, like that. Okay, so again, what did I do? I divided both sides here by 2 pi r, and that's the velocity is 10 meters per second divided by 2 times 3.14 for pi, put some spaces in there, times the radius, and the radius we found to be 714 meters, like that. Okay, and what's that going to equal? Well, we will find out. This is a terrible frequency, but there it is, okay? And this would be in hertz, okay? So a very, very low frequency. And that makes sense because, it's got such a huge radius. When you get frequencies that are that small, it doesn't make sense to talk in terms of frequency. Probably if I were giving you this problem on a test, I'd ask you what the period of the motion is. And of course, the period is just the reciprocal of the frequency. And that would be, let me give you that number, 448 seconds. Okay, so it would travel along a circle of radius 714 meters, really big. Okay, and it would take 448 seconds to make that turn. So 448 seconds, just to convert that to minutes, is going to be like 7.4 minutes. Okay. All right, there you go. So that answers that question. So like in the pre-recorded lecture, and I think on the assignment as well, I didn't give you a very large particle, like a macroscopic size particle. That's what this is. Something that has like a charge of 3 microcoulombs and a mass of 1.5 grams is like maybe a water droplet, okay? And I mean, I don't know how water droplet would be traveling at 10 meters per second, but something like that, okay? But normally you talk about cyclotron frequencies for small particles like protons or electrons that are fired into magnetic fields, and then they start to do their uniform circular motion. Okay, well, that ends this part of the stuff on a magnetic field, the stuff that we've done this week. Let me take a look here if there's any questions in the chat. 3 people watching, but doesn't seem to be any questions. Let me just ask, is everyone okay then? All right. And if no one responds, then we're done. Okay. It's difficult for me to divide, these topics into exact equals. So I would guessing that next week might be a bit more demanding. This week was a little bit lighter. Next week is going to be a little bit more demanding. Okay, we're going to return to the solenoid and look at inductance. Okay, and that is what happens when you put a solenoid in a circuit. Okay, and it acts, like just like you had RC circuits, that is a resistor and a capacitor in a circuit. What happens when you have an inductor and a resistor in a circuit? And we'll see what happens. Okay. So, okay, I'm not getting any answers here, and I'm assuming that everyone's okay. So, let's call it an evening. Good night, everyone.